Welcome, statistics students. We are now in chapter 10, and chapter 10 is where we start talking about what happens when you have two samples, and that's, if you think about it, that's actually a really big part of statistics, and it may be one of the largest things that we do in statistics are problems where we have two samples involved. What does this mean, and why would this be important? Well, if you think about doing science, what we often do is we take all of our population and split it into two groups and put it into a control and an experiment. And so if we have some sort of control and experiment, what you really have is two samples. You have the sample made up of your control items and the sample made up of your experimental items. And then what you're trying to do is find comparisons between that. Well, there are two ways of creating your two groups to make comparisons. One way is what we call independent samples. And you might be able to guess what we mean by independent. That word is kind of what it sounds like. Things that are independent don't impact each other. So independent samples do not influence each other's results. So this is the vast majority of all research studies that you would do. If you give someone a medication, so if one person gets a dose of medication to try to treat COVID-19 and another person doesn't get that treatment, whether or not the second person gets the treatment isn't going to affect the results of the first person. They're completely separated. So one person's health has no influence on another person's health. Similarly, if I give you all tests, if I were to give half of you one test and give another half of you the other test, how someone does on the first test does not affect how someone else does on the second test. That person's result in the test doesn't influence your answers. I hope it doesn't influence your answers. Otherwise, you're cheating. All right. So that's one way of doing tests, doing samples. The other way are when we have dependent samples. And dependent samples, for us, we're going to focus on one specific type of dependent samples, and that is when we have paired dependent samples. And paired just means that each individual in the first sample has a pairing with an individual in the second example that we would expect them, if there's, under the null hypothesis, if there's nothing interesting going on, we would expect them to have the same results. One of the most common examples of this is a before and after study. So notice if I give you all a pretest and then I give you a post-test, those who did really well in the pretest should do really well in the post-test. And those who did poorly on the pretest should probably also do poorly on the post-test, unless you actually learned something. So pretests and post-tests are a great example of dependent, because what you did the first time should be pretty close to what you did the last time, unless something changed. And what we're trying to do in statistics is figure out what that change might be. Similarly, you might, if you're doing a medical study, you might study a patient before and after you give them the medication. And then you'd have a pre and a post, and you would see how much changed. So, so dependent, paired. So think for example, pre-post tests. So pre-post tests are a great example of this. And this is going to be the example that we're going to do today. So the example we're going to do today, I use my school examples because I have trouble thinking of things that aren't teaching. And so a teacher gave 6 probability students 2 exams. The teacher gave them a pre-test and a post-test. And what the teacher is hoping is that the students' grades improved. Well, when we have paired sample, so this is dependent, paired dependent samples, and the reason they're dependent is because notice the pre and post test should be pretty similar. So if you scored pretty high on your pre-test, we'd expect you to score pretty high on your post-test, and low scores you would also expect to be kind of connected. Well, there's really going to be just one method that's going to make sense, and the method is this: make a column of differences. So what I'm going to do is I'm going to just add another line here, and all I'm going to do is just write the differences in this column. So in this line, let me erase this. just so I have space. I'm just going to take one of these minus the other one. And you can decide, do we want to take your post-test minus your pre-test or pre-test minus your post-test? You're going to get the same answers both ways, except one hand, they'll all be negative of the other one. So it just depends on whether positive or negative. That is going to affect how we do our study at the end, but it won't affect our answer and our conclusion and our results. So tell you what, I'm going to do my differences. I'm going to do my post minus my pre. So I'm going to do post minus my pre-test. Since I'm hoping their grades went up, I'm going to take the bigger one and subtract the smaller one from it. So I'm just going to make a column. And so 79 minus 75 is 4. Looks like I have 15 here. Negative 2, because that one actually went down. Negative 2 again, because that one went down. That one's a positive 2, and that one's 8. Now, once I have my column of differences, what I'm going to do is I'm going to ignore the first two columns, and I'm going to use that column only. And so what I'm going to do is I'm now going to erase my pre and post tests and just look at this column of differences. And now I'm going to do stats just like we would have done, just like chapter 9 with these numbers. So now we're just like chapter 9 again. So if you were able to solve all the problems for chapter 9, you should be just fine at this point. You make a column, we have these numbers, and we solve it. Okay, so how do we go about tackling a problem like this from chapter 9? Well, the first thing we do is we make our hypothesis. Our null hypothesis is that our null hypothesis would be that nothing has happened. So our null hypothesis would be that there's been no change in the grades. And what would we expect if there was no change in the grade? Well, if there's no change in the grade, we would expect the numbers to all be 0. So if the students did the exact same before and after, your differences would just be a whole column of zeros over here. So my null hypothesis is mu is equal to 0. And now my alternative hypothesis is, well, now I have to ask, what if the students did better on their post-test? Because I'm asking, did the class's performance improve? If they improved, then these numbers should be positive. Now, this is where, notice, I subtracted one direction. If you subtracted the other, if you subtracted pre minus post, then getting better means you have a negative number, and that means you would have a less than instead of a positive greater than. And other than that, the problem's going to work out the same. You're just going to use a different hypothesis and follow that hypothesis the rest of the way. Okay, so these are hypotheses. Now all I have to do is I have to pick my test. Do I want to use a Z or a T test? The answer is, so this was my hypotheses. The next thing I want is my test statistic. And am I going to do a Z or a T test? The answer is a T test because I have no idea what the standard deviation for this is. So I'm going to do a T test. And I'm going to do T is equal to, and then I'll use the same values that I had before, x bar minus mu divided by S over the square root of n. A few of these are going to be pretty easy. Mu obviously is 0 because it's that number, and so it's always going to be 0, so that goes in really easy. X bar and S, I'm going to have to use my calculator to find, and then n is just how many samples we had, and I had 1, 2, 3, 4, 5, 6, so I had 6 items, so n is 6, and X bar and S, I'm going to use calculator. Okay, so let's go type that in the calculator and see what we get. I'll try to hold this up where maybe you can see it. I'm going to go to Stat, Edit, maybe you can, who knows. And then I'll clear my L1s, and then I'm just going to type my numbers from my differences. So I had 4, 15, -2, -2, +2, and 8. Okay, so now that I have those, I will quit. Go to Stat, Calc, one variable statistics, and hit Enter. And it looks like I got 4.166 as my X bar. And it looks like I got 6.52 as my S. So 4.167 as my X bar, 6.52 as my S. And there's my results. So now all I have to do is put those numbers into my test statistic, and I'm well on my way to being successful. So now my test statistic is T is equal to 4.167. I could subtract 0 from it, divided by 6.52, divided by the square root of 6, and let's plug all that in and see what I get. 4.167 divided by, open parentheses, 6.52 divided by the square root of 6. Again, make sure I put all the bottom in parentheses. You don't want to get your order of operations messed up. And I got 1.65, 1.56. 565. There we go. So that's what I got for my t distribution. And so now I'm ready for my p-value. And so my p-value, as in all the other problems, I draw myself a little normal distribution. I put my value on here, 1.565, and I'm looking for that shaded part right here. So I'm going to use TCDF with this. I'm going to use my lower is going to be the 1.565. My upper is just going to be some really big number, whatever it is. And then my degrees of freedom is going to be, well, it's always one less than n, so my degrees of freedom is going to be 5. So I will now take all of this, put this in my TCDF button, distribution, TCDF, and then I'll put 1.565, comma, some gigantic number, comma 5, and hit enter. And I got 0.089 is what I got for my p-value. 0.089. Okay, so 0.089 is my number. So what I wanted to do was I wanted to determine what's my conclusion if alpha is equal to 0.05. So my conclusion with alpha equal to 0.05, well, I have to compare these. So what I see is I see that P is bigger than alpha. So I had, my number was too big, so that means I can't conclude anything. I can't make a conclusion. You have to be smaller than this number to make a conclusion. So small numbers are when we reject. So, so I fail to reject the null hypothesis. In practical terms, this means I do not have enough evidence to conclude, I'm almost here, I can get one more. Not enough evidence to conclude that the scores improved. Okay, so there's not enough evidence. Now notice if someone came to me, if a researcher came to me with this study and said, hey, I say these 6 students, do you think my tests are improving? What I would probably tell them is, you only had 6 people in your sample. And with only 6 people, your p-value was really close to 0.05. You can't write this up and send it to a paper. You don't have any, you don't have enough data to make a strong conclusion. But there's really it's really good evidence to think that maybe if you kept doing the study and you got the same results over and over again, that you would be able to make that conclusion. So I would go get more students. Instead of having 6, have 60. And if you could have 60 students and you get similar results, then you would definitely have a very, you definitely have a very small p-value, and you'd have something to go with. So that's all we're going to have for section 10.1. Section 10.1 is a fairly short section. If that concerns you, we'll make it up for it next time, because section 10.2 will be a little bit longer.